All right, so yesterday we talked about two main theories for acid-base chemistry. We're going to focus the majority of our time on Bronsted-Lowry's theory of acid-base chemistry, where we're discussing movement of protons. And just briefly to review yesterday, we said acids donate protons, bases accept protons. And after an acid gives up its proton, it becomes a conjugate base. And once a base accepts a proton, it becomes a conjugate acid. And like we saw in our problem of the day, stronger acids create more stable conjugate bases, and stronger bases create more stable conjugate acids. So it's this relationship that we have to look at with the overall equilibrium. And then we looked more carefully at the equilibrium, and we said we can define things using, or the equilibrium constant using these Ka values, where a large Ka is indicative of a strong acid, and we can measure that experimentally, and a small Ka is a weak acid. However, we saw in a real-world example, Ka values can go from giant, as in the case of HCl, to super tiny in the case of methane. So oftentimes chemists will use pKa to help narrow down that window that we're looking at. So instead of looking at ratios, we're looking at orders of magnitude. It's a really big difference. And pKa, if you remember, is negative log of the acid dissociation constant. So now what we need to do is look more at that equilibrium. And the equilibrium is really important. So we're going to draw this out. And it's going to seem silly to draw it out and explain it the way I am, but bear with me. So right now we have an acid. And we have a base. And like I said before, the base is going to reach over. Oh, let me change this. And grab a proton from the acid. And it's important to remember, it's only grabbing the proton, none of the electrons associated. The electrons in this covalent bond are going to end up getting dumped onto the atom A, or the conjugate base here. So A now has a negative charge, and then the proton is now covalently bound to B. And if we think about this proton, it's covalently bound to B through what used to be the lone pairs coming off of B, right? So now B, because of that, has a formal positive charge. So this is our conjugate base. And this is our conjugate acid. So again, kind of reviewing what we were looking at yesterday. However, there's something really important to consider, and that's that this is in equilibrium. And we've got two different acids in equilibrium. We've got our original acid and we've got our conjugate acid. Okay, this is an important thing to pay attention to. It's basically what's stronger, your original acid or your conjugate acid, right? The stronger acid is essentially going to win. So the stronger acid will push, that's the scientific term, the equilibrium to the other side. So for example, if HA is a stronger acid than our conjugate acid HB+, that means the equilibrium is going to favor the product side. But if HB+, that conjugate acid, is stronger than HA, then the starting material side will be favored over the product side. So we have to think about that. All right, so let's take a look at some simple examples. We'll do the easy ones first. We'll do HCl, hydrochloric acid, plus water. And I'll draw in all my lone pairs and covalent bonds so we can track where everything's moving. And I'm actually going to put a box here. We don't know which side's going to be favored. But we do know that HCl is an acid, hydrochloric acid by name. It's going to grab this proton, kick electrons to chlorine. That means we're going to have the chloride anion with a negative charge, plus the hydronium ion that has a positive charge. All right, so again, we've got to think about our acid. We know over here that this is going to be our acid. And over here, we've got our conjugate acid. So we've got these two competing acids in equilibrium. Oftentimes, chemists, what they'll do is they'll refer to experimental values in order to justify which side's going to be favored. And the experimental values that we like to use as organic chemists are pKa values. Instead of Ka values, it's just a lot easier. And you can often find these tables of pKa values. So I'll show you where to find that on my website. So on my website, if you go under useful links, and you go all the way down to pKa table and click on that, there's a pKa table from Dave Evans at Harvard. He's one of the most famous organic chemists alive, and he's helped compile a giant list of various pKa values. So really reliable, one of the most commonly used tables in existence. So let's use that table, and let's try to find HCl on here. And you can see in the left-hand column, we've got inorganic acids, which hydrochloric acid is. And we would highlight this and we'd say, all right, the pKa for HCl is -8, which is also what we saw yesterday. You may notice over here, there's a number in parentheses. That's for a different solvent system called DMSO, or dimethyl sulfoxide. That's often used for an acid that's simply not soluble in water, so you have to use a different solvent to test its acid strength, right? So in this case, HCl's got a pKa value of -8. So let's go ahead and plug that in. So pKa is going to be equal to -8.0, and that's an experimentally determined value. Next one we've got to do is look for the pKa of our conjugate acid. So we're looking for H3O plus. Luckily, it's listed right above that. It's -1.7. So we can plug that into our equation up here. All right, which is the stronger acid, HCl or the hydronium ion? HCl, it's got the smaller pKa value, right? So we can say, all right, smaller pKa equals more acidic than our hydronium ion. That means it's going to push the equilibrium to the product side, right? So oftentimes to show this, I like to show lopsided equilibrium arrows, where one side of the equilibrium arrow is pointing towards the product side. That's really big. The reverse side's pretty small. Oftentimes people have asked me too, I think somebody asked yesterday about one-way arrows. So maybe in Gen Chem you see it with a one-way arrow. That's typically the case anytime the difference in pKa values between your acid and conjugate acid is greater than 5, right? Because that means it's over 5 orders of magnitude difference. The reverse reaction, meaning favoring the starting materials, is really not that favorable. So the product side is going to be present like 99.999%. The starting material is going to be almost non-existent. So you can show this even as a one-way arrow if that difference is greater than 5. Yep. Yeah, it's an assumption. The reality is, like I said, the product side is going to be 99.9999999. That's still not 100. So if you talk to an analytical chemist, they'll be like, no, you're wrong. It's all a matter of how hard you want to argue about complete dissociation, right? It's kind of a semantic argument. All right. So the pKa tables are really handy. What I want you to do is to memorize all of these values for the first exam because you'll need them. That's a joke. I would never subject you to that. If I give you a problem on an exam and ask you something like this, I would give you the relative pKa values. The one I will say is really helpful to remember is the pKa value of water is about 15. Some people argue that it's 14. That's still an ongoing debate in chemistry that isn't resolved. Again, it depends who you're talking to. Analytical chemists hold very strong views. Physical chemists hold very strong views. And organic chemists hold very strong views. We don't have the greatest Thanksgivings together. All right, so like I said, don't worry about memorizing these. However, try to remember that water is about 14 or 15. That's a good benchmark value for everything else. All right. So moving on to the next thing, is let's say you're in a pinch and you have no pKa table and you're still trying to predict these things. It's going to be a lot harder, but we have some tricks. So how do we predict relative acidity? All right, just like I said before, you can always think of this as an equilibrium reaction between some sort of acid and some sort of base. And we always have some sort of conjugate base and some sort of conjugate acid that comes out. So this is going to be my generic thing, right? The key feature that we talked about with our problem of the day is that a really, really good, strong acid creates a really stable conjugate base. So stronger acids create more stable conjugate bases. The same could be true if we were drawing the equilibrium for a base, right? A really, really good base is going to create a more stable conjugate acid. So you can think of it inversely as well. But let's focus primarily on acids. That's what organic chemists like to do, is focus on the acid side. All right, there's various things that can stabilize a conjugate base, and I've got a good list for you. So various features can stabilize a conjugate base. And you can use this when assessing two relative acids, just like we did on our problem of the day. All right, I've got a good mnemonic for you. It's called cardio. And the I actually comes after the D, so bear with me. The first one is charge. So charge is really important. The I comes after the D, bear with me. It's not a perfect mnemonic, I'm working on it. All right, A is for atom. R is for resonance. D is for dipole induction. That's where the I comes from. And then O is for orbital. So you've got C, A, R, D, I, O in this specific order. If you read through the Klein textbook, he uses a slightly different one that he calls a Rio. He omits charge from there, which I think is really important, so I just made my own mnemonic, or I should say I borrowed it from somebody on the internet because I found it better. All right, if we look at this, we've got to compare these. Charge is typically the most important. And then orbitals are typically less important. This is a general good list of guidelines. However, there are exceptions to any sorts of rules in chemistry. I'm sure you're aware of that and pretty sick of it at this point, but this is a really good list of guidelines to follow. So let's take a look at charge first, and it makes perfect sense. It's going to seem pretty intuitive. Let's compare the hydronium ion to water. Which one is the stronger acid? The hydronium ion, right? And why is that? Because the oxygen is charged. It's like I'm giving away the answers. All right, so if you treat this with some sort of base, you've got this equilibrium. What's the conjugate base going to be for the hydronium reaction with a base? Water. Exactly. Once it loses its proton, it becomes water. So that's the conjugate base. And then the conjugate acid, in this case, is going to be Hb+. Do the same competing reaction down below with some imaginary base. We've got an equilibrium that we're looking at. What's the conjugate base going to be for this reaction? OH. So the hydroxide anion. I'm not going to draw lone pairs in here, but you get the idea. and then our conjugate acid. So really, when we're looking at this, like I said before, you can compare the stability of the conjugate bases. Which one's more stable? Water. So this one's more stable. So more stable conjugate base, simply because it's neutral, it doesn't have a charge. That means that this must be the stronger acid. All right, so anytime you're comparing two competing acids and trying to determine relatively which one's stronger than the other, you can set it up like this with some sort of imaginary base, and then analyze your conjugate base for each separate reaction and say, all right, which one's more stable? The more stable one is going to be the product of the stronger acid. All right, pretty intuitive for that one. It does get tricky as we move down the list. So number 2, we're going to look at atoms. And this makes more sense as we work through examples, but this is essentially branched out into 2 sub-areas. So the first one is electronegativity. All right, so let's do a couple of them. A couple simple examples. Let's compare water to methane. Same sort of comparison. We know intuitively which one's going to be more acidic. Water. Methane's a terrible acid. So if we treat this with some sort of imaginary base, we know water can be deprotonated, just like we saw above, form the hydroxide anion and a conjugate acid. Okay, versus the bottom one, we could treat this with the base. We saw that yesterday. It's not very likely. We said the probability of this reaction occurring in the forward direction is like finding one atom that's hidden on planet Earth. You might as well give up. So you got CH3 minus plus our conjugate acid. Just like we did before, we're going to be comparing our 2 conjugate bases. And in this case, electronegativity tells us more electronegative atoms are going to be happier carrying a negative charge, right? Which immediately means that OH minus is definitely going to be more stable, right? So this is going to be more stable due to the electronegativity. I'll abbreviate that as En of oxygen, right? That means conversely, water must be the stronger acid. If you notice, when we're looking at the 2 starting acids, there's no charge, and then the charge of the resulting products is the same, so we can't compare charge in this case, which means we move down the list to atoms. Yep?
Can we determine the pKa of the conjugate acid based on the pKa of the starting acid?
Not exactly. We'll talk more about that later, but yeah, it's not super simple. There's a lot going on. Okay, so electronegativity is the first half of that coin, right? Electronegativity is pretty important. You're familiar with that from general chemistry. The second side of this coin is atomic size. And, all right, if we think about electronegativity, does it increase as we go left to right or right to left along a row? It increases as you go right. So really with electronegativity, that's when you're comparing 2 atoms that are in rows. So I'd say row comparison. Atomic size is a bit different. That's when you're going up and down a column. All right, so let's take a look at the atomic size example. We've got a few that we can consider. So let's say we have hydrochloric acid versus hydroiodic acid. The question is, all right, which one's stronger and why? We're not looking at electronegativity because we're comparing chlorine and iodine, which are in the same column, not in the same row. So same idea. We're going to treat this with some sort of imaginary base. Draw out our equilibrium. And the conjugate base for the first reaction is going to be the chloride anion. Conjugate base for the hydroiodic reaction is going to be the iodide anion. And in each case, we get our conjugate acid. So now when we're looking at this, we're comparing the chloride anion as our conjugate base to the iodide anion as the conjugate base in the other reaction. Question is which one's more stable, and we're not invoking electronegativity because they're not in the same row. We really only use electronegativity when we're comparing across a row. All right, so now the question is which one's going to be happier carrying a negative charge, the small chloride anion or the really big iodide anion? Yeah, if I'm a negative charge, I want a big area to roam around in, right? I don't want to be forced into a little atomic cloud. I'd much rather be in a giant electron cloud. So in this case, iodide is more stable due to larger atomic size. That means hydroiodic acid must be the stronger acid. It's confusing. So when you're comparing up and down a row, so in this case, chloride versus iodide, you look at atomic size. If we go back up here, we were comparing oxygen with a negative charge to carbon with a negative charge. That's comparing across a row. That's when we look at electronegativity. Somebody should be raising their hand now and saying, what if they're not in the same row or the same column? What do you do then? It's kind of tricky. If they're not in the same row and not in the same column, that's typically when I pull out a pKa table, scratch my head, and try to find it on my own. It's not super intuitive at that point. So this really only works well if you're comparing things in the exact same row or the exact same column. Make sense? All right. Surprised nobody threw their hand up right away. All right. That's good. All right. So we've done C and A in our cardio rules. Now we're on R, which is resonance. We saw an example of resonance already in our problem of the day, but let's take a look at another example. And in this example, I'm going to compare ethanol, what we made in lab the other day, to this functional group, which is carboxylic acid. So we're comparing ethanol to a carboxylic acid. Intuitively, we can predict that the carboxylic acid, by its very name, is going to be more acidic than ethanol. But let's try to rationalize it a bit more. So same idea. Use some sort of imaginary base. And I'll even throw in arrow pushing for good measure. This base is going to grab this proton. Now this is our conjugate base with the negative charge, plus our imaginary conjugate acid over here. Same thing down here. Grab this, kick over electrons. Plus our conjugate acid. I forgot my negative charge right there. All right, so just like we were doing before, we're going to compare the conjugate base for each of these two competing acid base reactions and determine which one's more stable. And as you can tell by the name of the section, the one with resonance is going to be more stable. So what we can do is draw out the resonance structure for this bottom one. So I can say, hey, we can dump down these electrons, kick up those electrons, use double-headed arrows for this reaction, or not even reaction, the structure, excuse me. All right. If you want, you can even go one step further and draw the hybrid of your resonance structure, in which case you'll see that that negative charge is shared across both oxygen atoms, right? So now, when we look at this, we can say, well, the one where the negative charge is being shared across multiple atoms is obviously going to be a lot more stable as a conjugate base. So I'll just go ahead and circle this and say this is more stable since the negative charge is delocalized through resonance. That means, conversely, that this must be the stronger acid. Does that make sense? All right. So that's the R of the cardio rules. Next one we're going to look at is dipole induction and try to explain what's going on there. And dipole induction oftentimes goes by another name. It can be thought of as, oh my goodness, I'm completely blanking right now. I'm so used to using dipole induction. My brain's short-circuiting right now. I'll get back to you with the other name. I'm completely forgetting. Oh, oftentimes it's just referred to as induction. Holy cow. I was like, what is that? There we go. So it's often referred to as dipole induction or induction. Basically what this means is that it's pulling electron density through multiple sigma bonds. So let's take an example. We'll take a look at it. Let's consider this example of ethanol versus perfluorinated ethanol. The difference is instead of having hydrogen atoms on it, we've swapped them all out for fluorine atoms. All right. You can imagine each reaction reacting with some sort of imaginary base. All right. Perfluorinated compounds are actually really fascinating. If you study environmental chemistry, they're nasty stuff. They accumulate in the environment, build up in ecosystems, and cause all sorts of problems. I'll talk to you later about Teflon. Teflon has a bunch of carbon-fluorine bonds. I would encourage you to avoid using Teflon cookware as much as possible, and I'll get off my soapbox and start explaining dipole induction. All right. So I'm going to abbreviate. Actually, I'll just draw them all out. So we've got a negative charge on this oxygen, just like the other one. Let me scoot this over. The power of technology. All right. So if we look at each of these conjugate bases for the two competing reactions, we can go down the list and we can say, well, they have the same charge. Okay. Go down the list one more. When we look at the atom, well, the charge is both on oxygen, so we're tied at the atom level. And then we go down the list and we say, is there resonance? No resonance structures that we can draw. That's where dipole induction comes in. Which molecule do you think is going to be more stable and why?
The
Bottom one, why?
the fluorine's tugging on that negative charge. Super electric.
Yeah, so I heard somebody say fluorine's tugging on that negative charge because it's so electronegative. It's different than resonance, right? Resonance is complete delocalization to a completely new atom. This is more of a tugging feature. I like that word. All right, so you can think of it this way, right? The fluorines here are going to be pulling electron density away from that oxygen, and then the fluorines over here are also going to be pulling electron density away from that oxygen. So that tugging force by each of the fluorine atoms is basically stabilizing that negative charge a little bit. So let's draw this, say more stable. Due to electronegative fluorines tugging on the negative charge, right? That makes it a bit more stable. That means this is a stronger acid. Make sense? All right. There is a very important feature associated with this. So I'm going to give you a challenge. I think we have enough time. All right. Let's compare these two molecules. Actually, I'll stack them just to keep it consistent. These have the exact same molecular formula. So what are they referred to as? Isomers. What type of isomers? Constitutional isomers. So they're constitutional isomers. Which one's going to be more acidic? So again, we can imagine a base. So let's quickly draw this out. Oops, sorry. Should have a negative charge. Same thing down here. So again, what we're going to be looking at is this product, the conjugate base versus the bottom conjugate base. We could ask ourselves which one's more stable and why. Top one or bottom one's going to be more stable? Top one? Why? Yeah, because the fluorines are closer. If you're closer, you're going to have a disproportionate effect on your tugging ability, right? So in this case, the top one's going to be more stable. Since the fluorine is, or fluorines, I should say plural, are closer. That means that this one must be the stronger acid. You can also do the same thing. Let's say we were comparing chlorines in the same position to fluorines in the same position. The molecule containing the fluorines is going to have the more stable conjugate base. So there's distance and electronegativity that you both have to factor in. Yep.
So if it ends up being like one fluorine that's closer versus two fluorines that's further away, is that at that point can you not really compare them?
Yeah, so the question is, what if you're comparing one fluorine that's closer versus two fluorines that are farther away? That gets really tricky. I normally wouldn't expect you to know something like that. We're trying to compare essentially apples to apples here. Yep. Yeah.
Is what we decided is the does it have to do with how many fluorines there are, or just the fact that it's on the
So it is cumulative. So the question was, are we determining how many fluorines are there, and does that have an effect? Each fluorine you add adds a little bit more tugging or more stabilizing feature. So that does play a role. So fluorine being the most electronegative atom on the periodic table has a disproportionate pull. Hydrogen really doesn't have much electronegativity. In fact, the bond between carbon and hydrogen is typically thought of to be non-polar. So there's essentially no tug, versus fluorine, which has an incredible tug. Does that make sense?
Yeah.
Okay.
So then with every fluorine you add, it pulls a little bit.
Yeah, every fluorine you add pulls a little bit more, which stabilizes your conjugate base a little bit more. But distance to that negative charge matters. Yeah. All right. And then the last one we're going to look at today is orbitals. We'll go through this pretty quick. All right, with an orbital, let's compare two compounds. Let's compare methane to acetylene. Acetylene is commonly used in welding. In each of these, we're going to treat them with some imaginary base. We know from previous experience it's not easy to deprotonate methane, but you can draw the theoretical acid-base reaction. All right. If we deprotonate acetylene, same thing. And so what we want to do is we want to look at the orbital that the negative charge is contained in for each of these. So if we're comparing our conjugate bases for each of these, what orbital is the negative charge or lone pair going to be contained in for this one? SP? What about up here? It's got 4 electronic groups around that central carbon, so it must be sp3. All right, which one's the longer orbital, sp3 or sp? sp3 is much longer, right? If you're a negative charge, would you prefer to be further away from your positively charged nucleus or closer to your positively charged nucleus? Closer. So down here, we can quickly say this is more stable. Since the negative charge is held closer to the carbon nucleus. That means that acetylene must be the stronger acid. All right, that's where we're going to stop today. This is pretty tricky stuff. If you do have questions on your problem of the day, don't hesitate to stop by my office tomorrow. Did you have a quick question? Yeah, it's a bit weird. If you think about chloride, it's a point charge, so that negative charge can go around the entire atom. Versus this one, it's stuck in one orbital. Okay? And so because it's stuck in one orbital, the cloud size is about the same between sp and sp3. But it's closer to the nucleus of that